Right. Good afternoon, everyone. I took a look at the homeworks that have been submitted so far. Um, there's one question that many of you haven't addressed properly, which is marking the polarity for the inductor coil. So you've given the graphs for the voltage across the inductor and the current through the inductor, fine. But the voltage chart only makes sense if you mark it on an image what is positive, what is negative for the inductor. Right. So whenever you, I think it was for both the second problem and the last problem, we plotted the voltage and we plotted the current. But it only makes sense if you give what the polarity for the current is and then mark what the direction for the voltage is going to be. Right? Because if I choose this positive, negative, it can be look like this. If I swap it around, the same waveform can be negative. Right? So just drawing this plot alone is not sufficient. Draw the inductor diagram and make sure you draw the voltage and the current alone. Right? Otherwise, I think everything else looks fine. Does anybody have any questions with the homework? Okay. So we will continue with DC motors today, the construction. Next Wednesday, a couple of you in the online poll had requested that I do some kind of review exam or review the course material before exam or give a sample midterm. So instead of providing a sample midterm, what I'm going to do is we are going to review a couple of problems next Wednesday. So before you come for class next Wednesday, be prepared as if we are preparing for the exam. And when I do the review questions, if you do not know the answers for it, then you will struggle with the midterm, right? So just prepare beforehand, and during the review, we just go over a bunch of problems. The exam will be a little bit more complicated than the homework. It will be exactly the same four homeworks that you have done, but the problems will be twisted a little bit around. It will be made a little bit confusing. So if you understand the theory well, you'll sail right through it. If you don't understand the theory, you just kind of did the homework and memorized it, it'll definitely lead to getting a failing grade for that, right? So try to understand the theory. If you understand the theory, you'll be absolutely fine with the exam. Okay. So today we'll continue with the DC motor. So last class, on Wednesday, we looked at this hypothetical DC motor with some coil in between and some commutator segment and with some brushes outside. Practical DC motor, real world DC motors are not wound like this. We will have an iron core on which the coil is wound. Can somebody tell me why we would have an iron core for the rotor? Why not just put it in air? Let's say somehow mechanically I'm able to make it stable. Why use an iron core to wind the rotor? So going forward for the rotor, I'm going to use the term armature. That's the standard term used. Again, it comes from the horseshoe magnets plate, which was also called armature. That should give you an answer as to why we need the iron core. Anybody? There are two problems that the iron core addresses.
More conductive magnetic fields.
All right, and why do we need more conductive magnetic fields? Why do we need a ferromagnetic material there? We did see a sample problem, and it was there in your homework too, right? Without the iron, what is going to happen to the magnetic field of the magnet? It's going to plummet, right? So when you have a very large air gap, you did the load line graph for a magnet. So this was your magnetic field for the magnet. And if this is for some LG1, then this would be the line for 2LG1. So if the air gap length increases, the slope becomes smaller and smaller. That means the point where it intersects the BH curve would become smaller and smaller, and the magnetic field in the air gap is going to be significantly lower. That's the reason you want to put that iron core inside so that you reduce the air gap as much as possible. So all of the rotor structure would be wound on an iron core so that you can push this line as high as possible so that you have as large a magnetic field as possible. Why do you need a very large magnetic field? What are we trying to achieve by putting a very large magnetic field? What will happen if I had a very low magnetic field? What is going to be the effect of it? When we looked at a torque expression, right, we had a torque expression which was 2RL and B times I times cos of alpha for the single coil, assuming alpha is this angle with respect to the B field and the coil. So if my B goes down, then my I has to go up to produce the same amount of torque. Right? So if I want the same performance in a motor, one in air gap, one with iron core, the one in air gap, the B field would be enormously small. That means the I must be extremely large. And if I is large, that means you're going to have a lot of losses in your motor. Right? That's the one bigger problem with we have, because all of these are copper wire, but they are still a very long wires. So they will have significant amount of resistance. And then we have these brushes, which have quite a bit of resistance, and then the wires that come out, all of these resistance add up. And that means if a current is very high, the total power loss in your motor will be very high and efficiency will come down. Yep, Ben.
Is the armature still, you said the armature is the coil or the?
Armature is the rotor structure. The full thing is called an armature. When we talk about the coil, we call it armature winding or armature coil.
So if the magnets are rotating, the armature is still?
The magnets aren't rotating. The rotor is the one. Armature is the one that's rotating.
But in some motors, the magnets will rotate, correct?
That'll be in the AC motor.
Alright, sure.
Not in the DC motor. Right? In DC motor, we will have these fixed because we have this mechanism for current to commute. When we go to AC motors, we can do the same commutation by putting AC currents. So we can move these windings to the stator and then put the rotor magnets on the rotor. Right? Any questions? Okay, so that's the reason we want to put an iron core. That's the first one. Second one is not too very obvious. Can anybody think of any other reasons why we want to put the iron core? All right, so let's look at what the field lines look like when we have these magnets alone. Right, so we had these field lines going straight because that was the path of least reluctance. Right, field lines going straight from the north pole to the south pole. And then when our winding was at say some odd angle, 45 degrees. Right, so with respect to the field line, let's call this angle as 45 degree. We computed what this force is going to be. That's how we got the torque expression. And only a component of this force is going towards torque. There is a component of force that is just pulling the wire outwards, and there is a component of force that's producing the torque. Right. So this is the actual force from the Lorentz force equation, LIV. But only a component of this is actually producing torque. And this is because the field lines are in this direction, while the conductor is not in the same direction as the field line. So if the field lines are always perpendicular to the conductor. So let's look at what will happen once we put a rotor structure. Right, and then we have an iron core in the middle, and we have conductors in the slot of this rotor iron core, armature iron core. 1, 2, 3, 4, 5, 6. I mean, to make it even. It will always be even. So we have these conductors coming from inside. So this is a 2D diagram looking from the top of it. So conductors are in this direction, and then we have a magnetic field in this direction going from here to here, here to here. And this force, of course, is going to be perpendicular depending on the direction of the current. Let me say the current is going inside here, coming outside here. So torque is going to be downwards here, torque is going to be upwards here. Sorry. Yes. When it comes out, magnetically like this, I cross B would be upwards, and then the opposite would be downwards. What will be the direction of the magnetic field on this conductor? This is, let's say, permeability is infinite. Would the field line still look like this? Will the field line still go parallel from north to south? Is that the path of least reluctance for the magnetic field? Whenever you have two surfaces, right, let's say I had a surface like this, the least reluctance would be effectively the shortest distance, right? The point where the gradient is going to be your minima. So it is always going to be the perpendicular direction from one surface to the other surface. That is where you're going to have the path of lowest distance, right? Lowest distance, smaller the distance means smaller the reluctance. So once you put an iron gap, the magnetic fields are not going to go straight like this, because previously This was the path of these reluctance. The shortest distance is the best path. Now the shortest distance is different. It is the one going perpendicular from this face of the magnet to the iron core. Okay, so this is going to be the path for these reluctance. So on the surface of the iron core, the B fields are going to be perpendicular. And this happens with any kind of surface that you have. If you have an odd looking surface like this, and you have some external magnetic field, all of those magnetic field lines will terminate perpendicular to the iron core. Okay? Doesn't matter what kind of structure you have, assuming the permeability is very large. Right? This is similar to when you did the case for electrostatic analysis in your electromagnetic theory course. If you had a spherical conductor and you had some electric field external coming from, say, a parallel plate or something, once it approaches the sphere, they would all terminate perpendicular to the sphere. Right? If it is not terminating perpendicular to the sphere, there is going to be a tangential component, and the sphere being a conductive material is going to have a lot of free charge. The tangential component is going to pull the charges apart and spread them out so that only the perpendicular component exists. Otherwise, if there's tangential component, it's going to create circulating currents. Right? So that's how it gets eliminated there. So you can do the same explanation here too. Inside the iron core, the H field is going to be very close to zero because mu r is infinite. If say the B field is 1.2 Tesla, B divided by mu r times mu naught is going to be your H. H is going to be very close to zero. If H is zero, integral H dot dl, which is the current enclosed, that part is zero too. Right? So there is no circulating current on the inside. So the H field is going to be zero, so that there's going to be no tangential component of H field, which means there's going to be no tangential component of B fields. All the B fields are going to be perpendicular. It's the same mechanism, different formula. So, right? So whenever we have this iron core, we have these B fields which are perpendicular to the conductor in every direction. That means our formula for torque loses this cos alpha term. Right? That's a huge saving. So previously, there's only a component of torque that was component of force that was pulling, creating rotational torque. Now all component is pulled making rotational torque because there is B field in this direction, current is going into the page, and the torque is going to be perpendicular to both of us. So current is like this, B field is like this. The perpendicular component is the tangential component to the surface. So that is going to be our torque. And again, this conductor, it's tangential component. This conductor, right? The force is all purely perpendicular component. So the torque, all of it gets converted into torque. There is no cos alpha reduction depending on the location of the conductor that we have, right? Everybody clear on this part? Yep, Thomas.
So if you only made it so it was two conductors, that would still hold true, right? I mean, until like it reaches where, like the bottom where there isn't really north or south.
Yeah, no, at every single point, it doesn't matter how many conductors, you don't need a conductor at all. Let's just say remove out all of these conductors. If you just had an iron sphere, iron cylinder, all these lines would terminate perpendicular. At the top part too, they would terminate perpendicular, but it's just that the magnitude would be very tiny.
Okay.
Right, so every point it will all start parallel from the magnets, but then when they come to the ferromagnetic material, they'll all terminate perpendicular. Similar to this case, when you have parallel plate capacitor, you can have any magnetic field, however structure you want. You could have started them parallel. You can have some variations as they come along, but once they meet the conductive sphere, they all terminate perpendicular. Same thing happens with the iron sphere. Right? Any other questions? Okay. So this subtle difference kind of makes the torque significantly larger, right? But putting this iron, what problem do we get into though? When we had air gap, we didn't have a problem that gets introduced when we put this iron core. What happens as this iron core rotates? Initially it's seeing north pole, then it's seeing south pole, then north pole, south pole. Whenever we have varying magnetic field, what are the two things that happens on the iron surface?
Induced current.
Induced current. So we have eddy current losses, which we saw last class. Right? So whenever these magnetic fields are changing, the surface of the iron is going to experience some changing magnetic field, a magnetic flux, which is then going to create an EMF. Because of the EMF, current is going to start to flow on the surface of the conductor, or surface of the iron core, which in turn is going to be lost as heat. What is the other loss that we experience?
Hysteresis loss.
Hysteresis loss. So the changing flux created an electric EMF, which was lost, and then the hysteresis loss comes from the fact that the ion is going through the cycle. Right? Every time the B field changes, the ion is going through the cycle, and whatever area under this curve, that is being lost as your hysteretic loss. This is something that we can't do anything about, except ensuring that the material that we choose for our core has a very small width. Right? That's the only way we can avoid having a huge hysteresis loss. So there are two types of materials: hard ferromagnetic material and soft ferromagnetic material. So hard ferromagnetic materials would be materials which are good for magnets, right? Which is what we saw last week, where they had these huge BH curve, so that their coercivity is very large, and also their B field doesn't drop too much. So even with a significantly large air gap, you can get sufficiently large B field. But when you have soft ferromagnetic materials, you want this area to be as small as possible, right? So that the area under this curve is very small. So that while going through the cycle, you don't lose that much energy, right? So we introduced these two losses, but hysteresis we manage by choosing the right material with this tiny structure. So that is why when we use these iron, whenever I call iron for these magnetic circuits, it's actually silicon iron, or it's also called electrical steel in common parlance. So basically, when you have iron, typically when you have stainless steel, you have a lot of carbon injected into it, around 4%, I think. But when we create it for to make it very ferromagnetic, stainless steel, as you know from experience, is not not too ferromagnetic, right? If you take it near a magnet, your spoon won't stick to the magnet. So all you have to do is replace the carbon with the silicon in the structure, and depending on how much silicon you introduce, basically this width starts to narrow down, as well as your mu r starts to increase, right? And the purer you can make, reduce the amount of carbon and substitute them with silicon, the higher mu r you can get, and the narrower you can get for your BH curve. All right, so these two problems are introduced. How do we address the first problem, the eddy current issue? So by choosing the right material, we can address hysteresis. What do we do for addressing eddy current? Yep.
Instead of having like a big old solid block of iron, you just do a bunch of little plates stacked on top of each other.
Okay. So instead of having this very large blocks, right? So let's say this is the side view looking from the bottom, what the core looks like. Cut them into tiny, tiny slices and laminate them. Each of these plates are laminated so that whatever EMF is induced on first plate cannot draw push current into the second plate. So it's contained within this tiny area. And we looked at what that loss would be in that particular structure. All right. So going forward, we are going to be looking at this structure. So our torque equation, we'll rederive it. So this equation that we had was for the hypothetical motor, a simple case, but in reality, it'll be a little bit different. Just the cos alpha term gets dropped, and the EMF profile will also become a bit different. So previously, our torque varied. So in our previous case, when we had air gap, everything was there was no ion. Our torque waveform looked like this, but now our torque waveform, irrespective of the angle, the torque is going to be the same. So torque is going to look almost a constant, okay, except at these points where it starts to dip. And can anybody tell me why it dips around those regions? Thomas, you already gave me the answer in a different question.
In between the north and the south.
In between the north and the south, when we looked at our rotor structure, stator structure that I passed around last class, we saw that the magnet did not enclose the full 180 degree. Right? There was a small portion on the top where the magnet wasn't covering, the small portion on the bottom where the magnet wasn't covering. So in those regions, the B field is going to be very, very small. There is a very important reason why we don't do a full coverage, to reduce the armature reaction, which we will look at after spring break. But this is what the magnet look like. So the B field on the top is very small. Right? B is very close to 0 on the top. So when the conductor is around this region, right, or when it's exactly in the middle, north and south equally pull in both directions, so the torque goes to 0. But even on the top region, a little bit farther on one side or the other side, the B field is very small. So there is a dip in the torque that's produced. Right? Okay, so today's class we'll continue with looking at the structure of the motor, structure of the DC motor, armature, and we'll look at how to wind the winding for it. Right? Anybody have any questions so far? Yep, Thomas.
What was the flat part about?
The flat part is, so this was the torque previously, right? Because it was varying as cos of alpha.
Mhm.
Now the cos of alpha term is gone. The torque is constant, irrespective of the angle.
Right.
Right? It starts to dip only when the conductor goes out of the reach of the magnetic field or magnetic field lines start to weaken. Because here, this would be the shortest path, but the field lines would take this path because mu r is not perfectly infinite. Right? So the field lines would go like this too. But that path is slightly longer, that means the B field would be slightly lower. And then once it goes to the very extreme, it's going to be almost close to zero at that point. So around those regions start to drop, but rest of the region between here to here, wherever the full magnet coverage is, every field line is perpendicular to the conductor, so irrespective of the point, it is the torque experience is the same. Any other questions?
So if you have like way more conductors, does that ripple go down, or is it less pronounced? Or I don't know if that's the right word. Does it like not go to zero basically?
It will always go to zero. It has nothing to do with the number of conductors that you have.
Okay.
It is just to do, so this is, so the diagram that I've drawn here is for a single coil, right? So this is tau of one coil. So this is the torque of one coil, not n number of coils.
Right, okay.
So when you put n number of coils in the previous case, right, we had, due to the second coil, it was like this, and then the total actual torque was just the
Right,
cup on
that's-
top of it.
Okay.
So same thing would happen here too. So in this case, it gets a little bit more interesting because here, let's say the second coil torque looks like this. Right, the net effect of this would look like this. So, right, so you'll have those dips because whenever it dips, it's basically the average of this and zero, right? But if you have, say, 20 different coils spread around the rotor, this dip can be minimized to a very large extent, right? So the torque pulsation would not happen. Any other questions? Okay, so today's class, let's look at how to wind this rotor armature. It is a little bit tricky to get it in the, to get a full feel for it in the first time you're looking at the diagram. But I have posted the slides online. So go back and open it and look at it again and again. And homework assignment I posted. Don't worry, it is not due until after spring break. So after the Thursday after spring break is when it's due. So whenever you do the homework, you will it will reinforce how these windings work. But for now, let me show you how it's wound. Then we'll take it from there. So our rotor structure. So I'm going to draw two different views, the top view of the rotor and the bottom view of the rotor. So for this example, we are going to consider a 6-slot rotor. So what that means is on the rotor structure, so this is the top view. So the rotor extends all the way to the back of the board, right? And this is the bottom view. So this is top. And this is bottom. So in this case, you're looking as if the rotor is extending all the way to the front of the board and you're looking at it from the back side of the board, right? So the view we are looking at it is different. So this is a rotor structure. So this view is the top view, looking at it from here. And this view is the bottom view, looking at it from here. So it's going to be mirror symmetric, right? So when I say slot 1 is here, and let's say this is the slot 4. Let me go clockwise. Slot 2 is here. Oh, slot 3 is here. Again, these are all equidistant, so this angle would be 183 slots, 180 degrees, so 60 degrees away. The way I draw it might not make it too clear, but the separation between the two slots would be 60 degrees. Right? So for simplicity, let me not put the angle. So the other slot is here, and then the other slot is here. So 1, 2, 3, 4, 5. We have 6 slots on the rotor. Again, these are just so the way they would manufacture is actually take a cylindrical block of iron, silicon steel, and then cut it into slices like you would do like a bread loaf or something. And then they will stamp these holes into each of those individual rings that they have created, and then put a varnish or some kind of lamination, typically varnish, And then they would stack all of these together, weld at the edges or put some epoxy glue. Different things have different advantages, disadvantages regarding stresses it creates. And then through the middle, they'll put the rotor rod, and that's how they'll construct the rotor. Right, so this is the top. And in the bottom view, again, we have slot 1 on the top, slot 4 on the bottom. And then, of course, since I'm looking at it, so this was slot 1, this is slot 4, 2, 3, 5, and 6. When I see the same thing from the bottom, it is going to look in the opposite direction. Right? So that's all. There is nothing magical about this here. Second slot comes here. Third slot comes here. Again, this is the bottom view. That's why the numbering is different. Fifth slot comes here. Sixth slot comes here. So we're going to track how these windings are wound going from one slot to the other. Let me see if I can use different colors. So let's start off with the first conductor. So the first conductor, so this is again the top view. So the first conductor is coming from the back of the board and coming outwards. And then we take that same wire. So it's just a single wire. So throughout this winding diagram, there is just one wire, right? The way I'm drawing it is as multiple different conductors, just so that you can visualize how this wiring goes around. But it's just a single wire that the machine winds multiple different times. At no point does the wire break. Right? So we start off with the first conductor in the slot, and the convention is if it's a dot coming out of the board, if it's a cross going in to the board. All right, so conductor 1 is coming out of the page. The same conductor looking from the bottom view would look as if it's going into the page. Right? So if the conductor is coming out of first slot from the top view, from the bottom view, it would look as if it's going into the page. Right? So it's coming out of the top slot, first slot, and going into 180 degree away into the fourth slot. So the conductor comes out, you wind it on the top, and then pull it back into the slot and take it all the way down. Right? So the conductor came from the first slot, you had a wire coming on top, and then coming down, and then it's going into the fourth slot on the other side, 180 degree away. So this is called a full pitch winding. Full pitch. There are other kind of windings too. When you do the project, we will look at a case where instead of going from slot 1 to slot 4, we can go from slot 1 to slot 5. All right. We will look at what the advantages of it are a little bit later and what the disadvantages are. So does anybody know what the name of this stretch of the conductor is called? Is this stretch of the conductor useful at all? The one going on top of the rotor. So say this is the rotor. My magnetic field is all along this direction. There is a conductor that's going parallel to the magnetic field. Is that conductor useful at all? No, right? So these are called end turns. End turns. Right? It happens on the top, and similarly when we do in the bottom, there is a bunch of end turns. So when you saw the rotor structure last class, you'd have seen a whole bunch of conductors on the top. Those are quite useless to produce torque, and they do create quite a bit of leakage inductance, which is kind of have a negative effect on the motor operation. But in our case, we're looking at very ideal, simple case, so you're not going to worry about it. But these windings are called the end turns, which are useless for torque production. So what can anybody think of what would be the advantage of, instead of going from slot 1 to 4, what would be the advantage if I went from slot 1 to 5? What will be the length of the conductor going from slot 1 to 4 versus the conductor going from slot 1 to 5, which will be larger? 1 to 4, right? Because that's diametrically opposite. So I already said the end turn is useless, and I already told copper is expensive. So if you can reduce the length of this copper, you would go for that option, right? But this does have its own disadvantages, which would reduce the torque production. Because some portion of the time, this conductor and this conductor would be under the same magnetic field instead of being on the opposite magnetic field, which will reduce the torque. But in our hardware, in the lab motors that you saw, it is actually a bit short pitched, and we'll look at it, how it helps in aiding armature, why the solution for solving armature reaction would make it better to make it short pitch. For now, we're looking at full pitch. Full pitch means when we start at one slot, we end at diametrically opposite slot. right? That's all the term full pitch means, okay? So we started from, so the conductor comes from slot 1, goes into slot 4 in the bottom view, that is going to appear as if it is coming out of slot 4, okay? Now what we are going to do is once we come to slot 4, we are going to take it, we can do, one thing we can do is we can do this winding multiple times, going from slot 1 to slot 4, slot 1 to slot 4, slot 1 to slot 4, all right? So each of the slots that you saw on the motor that I passed around, you would have seen multiple number of turns going from one slot to the other. So whenever I draw this line, it is indicative of say 10 or 20 or 30 number of conductors doing the same winding in the same slot, right? When I use a different line, that means it's a whole bunch of different set of conductors going into a different slot. Okay, just to keep the diagram clear, whenever you see this winding diagram, they would usually only show one wire, but that is indicative of a whole bunch of conductor turns in that one particular slot. All of those indicating that one single line that I've drawn here. Okay, so once we are done with slot 1, we are going to go to slot, sorry. So the wire coming out of conductor 1 now, so coming out of slot 4 goes into slot 2. So going into slot 2, and then on the top view, it's going to come out of slot 2. Right? Once it comes out of slot 2, which slot should it go to? Yes, Thomas. Oh, 5. So it's going to, sorry, different color. So once it comes out of slot 2, it goes into slot 5. Out of slot 2 goes into slot 5. Right? Because on the top, it's always full pitched. Right? It's always 180 degree when you look at the top view. In the bottom view, we have multiple options. We can go from slot 4 to slot 2, or we can also do slot 4 to slot 6. Right? There are multiple different option winding. One is called progressive winding, one is called retrogressive winding. So if you wind backwards, it will create the same motor exactly. It will just confuse the heck out of me going the reverse direction, so I'm not going to do that direction. But going the forward direction is called progressive winding, going the backward direction is called retrogressive winding. For this simple case that we're looking at, both of it would create the same pattern. All right, in different complicated structures, it will be a little bit more different. And then there are other options too. So on the top, again, I said full pitch, 180 degree, right? Short pitch, I could do something smaller. In the back too, I can do the same thing. Instead of going one slot ahead of the previous conductor, I can go 2 slots ahead of the previous conductor. So there is a term for that. The winding you're going to be looking at is called simplex winding. Simplex. Progressive wound. Progressive lap winding. Right? So there are multiple options in which you can wind the DC motors. All of it have different advantages, disadvantages. Throughout this course, we are going to look at just the simplex progressive lap winding. Right? There are other ones. So again, lap winding is the case where we start from one slot, go to the next slot, and then go back to a slot in front of it. But I can rather do it to the forward direction. I can go from 1 to 4, from 4 I can go to 5, and then come back to 2. So there are multiple different ways, right? So lap winding is, once I draw a planar diagram, the difference between lap and wave winding will be clear. But in the circular diagram, it's a little bit more complicated to visualize it. All right, so for now, the diagram we're looking at the simplest progressive lap winding, right? Each of those terms have a reason and meaning to it. So let's see where did we stop. So we have 5 going in this diagram, 5 must be coming out. From 5, where does the conductor go? In the back view. I know it's quite a bit confusing the first time around, so don't get too startled. Just make a guess, where will it go? 3, perfect. Same as this, right? From 1 to 4, and then 4 went to one slot behind, one slot after 1. Now we are at 5, go one slot after 2. So we are going to go to slot number 3. So it's going into slot number 3. And then on the top view, of course, it's going to come out of slot number 3. On the top view, goes from slot number 3 to 6, perfect. So it goes from slot number 3, so it's always 180-degree opposite on the top, again, for full pitch. So I need to make that very clear, there are other possibilities too. So from 6, so looking back at the back view again, so on 6, so top view it went into 6, bottom view when I look at it from here, it will appear as if it is coming out of 6, perfect. From 6, where do I take it? What was it?
4.
4, thank you. So from 6. So from 6, I take it to 4. Now it does get quite a bit interesting. So we have a conductor going into 4, and we have another conductor coming out of 4. Is that going to be a problem? Will the torque produced by each of those cancel them out? If you have one conductor coming into the board, another conductor going out of the board, those of you are saying no. Why would it not cancel each other out?
Happening at different times.
These are all conductors present in the motor, right? All of them are going to carry current through them. And we said it's a single wire that's going through all of those. Yep.
Depends on how you wire it at the commutator.
Perfect. So it depends on which direction the current goes. This is just the direction of the conductor. This is not indicative of the direction of the current. So this is a conductor that's coming out of the board. This is a conductor going into the board. But if I set up the commutator in such a way that the current for the conductor coming out of the board is also coming out, and for the current conductor going in is also coming out, then both of these are going to produce a torque in the same direction or force in the same direction. If it ends up being that the current going in, conductor going in also has current going in, and conductor coming out has current coming out, then both of the flux, the magnetic fields will cancel each other. There will be no torque. Right. So when I set up the commutator, I need to ensure that current in these two are in such a direction that the torque is going to be additive, not subtractive. Okay. So where was I? Okay. So 6 to 4. So going into 4 on the bottom, coming out of 4 on the top. Where does it go from 4 on the top? Ben?
1.
1. Okay. So 1. So 4 to 1. And then once we are at 1, coming out of 1, going to Yes.
5.
perfect. You're all way better than me at this because the first time I did it, I got super confused. So going into 5, 1 to 5, coming out of 5, going to from 5 to. On the top, the rule is very simple. Where is it going to go from 5 to
2.
2. So 5 to 2. Okay, so then again, coming out of 2 on the bottom view, and then it is going to go into different color. I used everyone. Right. 2 reds close to mix. Back to purple. Green. So it goes from the two greens together. This is a nightmare. There is a mathematical problem. I don't know if you have seen where you have different maps and you need to pick a color so that no two states, contiguous states have the same color. It's a nice problem. I don't know if there's a solution for that yet, theoretical proof for it. I don't remember what I chose, I can't win here. So it's going for 6. What did I choose? So 6. Coming out, 6 2 on the top again, it's straightforward, goes to 3, right? 180 degree. Now something interesting happens. We have 3. Direction will go from 3
Commutator.
to the, I haven't drawn the commutator. All of those conductors need to go to the commutator, right? But is there a one? Keep following the rule. That's it. We have closed a full loop. All right, it's a single wire. It is not, these wires are not what comes out. So this is so the answer Ben gave, I assume your reasoning was this will go to the one terminal, this will go to the other terminal. But that is not how the windings work, as we'll see in a minute. All right, the wires are not what directly connect to the motor, the commutator, the external world, the commutators are what connects to the external world. All right, so whatever you look at the rotor, it is actually one full loop. If you were to take out the winding and lay it flat, it will be one full closed loop. That's it. So wherever we started, we have to end with the same loop closing the full thing. Okay, so this, I'm going to introduce another term, bear with me, it's called double layer. Because each slot has one set of conductor which is going in and another set of conductors which are coming out. Just a second. So typically when you have these DC motors, we will wind it in such a way this double layer is formed. Even when we have AC motors, we'll try to do this double layer, and there are different ways of winding this in machines. So that the top layer on one is hidden behind the bottom layer of the other. On the opposite side, the bottom layer is hidden behind the top, so that when the rotor rotates, centrifugal forces, if it pulls on one conductor, it will pull on the other one to go inside the rotor. Right? So it's more mechanically stable as the rotor rotates. So typically you would have double layer windings. And it's simple too, because a single layer winding would require a different kind of slot arrangement so that the starting conductor terminates with the beginning conductor. In our previous case, we couldn't have terminated the starting with the beginning because they were going in opposite directions. But in this case, it ended up being that the final conductor which is coming out ends up going into the page of the first conductor, which is what we started out with doing, right? So it kind of nicely aligned up. But there are other layers as well. You can do single layer or double layer. We typically you would see double layers in motors, right? Yeah, Ben.
Is there a reason why you don't go to the adjacent slot? You're talking about minimizing copper. You jump 2 slots. Is that just the convention for this winding type?
So going from, you mean,
Yeah,
so
like,
when we go back?
yeah.
Yeah, we can do it. That's a very good question. So when I draw the planar diagram, it will become much more clear, but you may be able to see it already here. The commutator segments would end up being in such a way that the brush would slide past first slot, conductors in the first slot to conductor in the second slot. If it were to instead slide to commutator from first slot to third slot, that wouldn't be mechanically possible. Right? In that case, what would then happen is these two would have to be in such a way that they are very similar voltage potentials. So you would have a very large brush that would slide past 2 commutator segments at once. Right? So it gets a little bit trickier. And that would be, instead of simplex, that would be a duplex winding. All right, those exist too. So in our case, we are looking at very simple case. So we are always going to assume that going from this slot to this slot to this slot to this slot, we can of course jump to 2 slots forward too. That will create its own advantages, that's its own disadvantages, right? But once I lay it out in a flat manner, this diagram will become far more clear. Any other questions? Yeah.
Are they always labeled clockwise as seen from the top? Like, is
No,
that the
that's just a random. Yeah, you can do it however you want. Again, so I just randomly chose it like this. Yeah, you could have chosen 1, 2, 3 like this and gone the different way. The way I chose it, I'm calling this as progressive, retrogressive, and so on and so forth. Okay, once I put in the parallel way, it will become far more clear what retrogressive and progressive is. But any other questions? Okay, fantastic. So let's. So this is what we saw last class, right? So we have conductor from slot 1 to slot 4 in the top, right? And then this is the bottom view. In the bottom view, it goes from 4 to, I need to look at 4 to 2, right? 4 to 2. And then rest of it, you can just trace it all the way down. So 2 to 5, then 5 to 3, so on and so forth on the bottom. So the bottom ends up looking like this, right? A whole bunch of star that's created. And then we are going to put the commutator segments wherever these bends are. Right, and then have the brushes placed in them. So wherever these bends are on the bottom side of the conductor, that is where we are going to put the commutator segments for each of those, and then we'll place the brush appropriately. Right. So let me go back to this. Let's see what how do we place the commutator segments. So I should have drawn it in such a way that the image came out circular. I'm not too good at it. But, so the commutator segments would be here. They are touching the wire. So wherever it's touching, that's where you saw when the wire is wound, there's a hook that's created. Onto that hook, the commutator goes in and comes out. On Canvas, I posted a link where it shows the image of the hook with the commutator segment separately, how the wire goes and hooks onto it. Typically, sometimes they solder it, sometimes they just remove the varnish and mechanical press it so that it makes electrical contact. And then we put our brushes here. Right? So this is where the current and the voltage and all of those would come into the picture. Okay, so let's draw the same thing that we drew it in the circular form in a way that's typically drawn in Machine's book, which is basically cutting this rotor structure out and visualizing it in a parallel manner. So let's see. Whatever diagram I drew there, now what I'm going to do is draw it in a parallel manner. So this is slot 1, this is slot 2, slot 3. So this section that's vacant, that's the slot. Slot 4, slot 5, slot 6. So this is a cylindrical structure that I've broken open, right, to visualize it and then laid it out flat. So what will come after slot 6? 1. So we go back again to slot 1, right? It's a think of you always need to think of it like this closing back on itself. So whatever it starts, it ends here. So when I draw the wiring, once the wiring I extend it here, that means it's actually coming from this side of the board and closing it back in again. Okay. So whenever I ask for winding diagram, this is what we need to draw. This is what all textbooks would draw. It's very intuitive in explaining what's going on. Okay. So let's start off with our first conductor. So whenever the conductor is coming out on the top layer, I'm going to use a solid line. Whenever the conductor is going into from the top layer, I'm going to use a dotted line. That's the convention I'm going to be using. So solid is out on top view, and then dotted is in on the top view, right? So first conductor is coming out of the top in slot 1. And then where is going the first conductor? 4. Thank you. And according to my convention, I'm going to use dot when it goes into the slot. Right? Okay. Where is this conductor now going? The one coming into slot 4. Where is it going to go next? Look at the bottom view, right? So here I drew the top view. So this section is the top view, and this is going to be whatever is in the bottom view. So where does conductor, the red one, so starting from slot 1, it went to slot 4 on the top, and then the conductor in slot 4, where did it go to in the bottom view? 2. Thank you so much. And I'm not sure what color I chose. 2 is purple. Oh, it comes out of 2 on the top view. Right? So this is what the progressive term of the progressive winding means. So going from slot 1 is going to slot 2. There is another way I could have wound it. Instead of going from here, I could have taken it to slot 6. Right? That would be called retrogressive winding. All right. So there are different ways in which we can wind it. And then going to Ben, your question, if I instead took it to slot 3 here instead of going to slot 2, that would be a duplex winding. Okay. Once I draw the commutator, you'll see what the trouble with that structure would be. It is used though. Okay, from slot 4, where is it going? sorry, from slot 2, the conductor on the top, where is it going? On the top, it's always 180 degree apart, right? So in case of our 6-slot machine, what is 180 degree apart? 3 slots away. So starting from slot 2, where should it go? Slot 5, thank you. Okay, and in the bottom, from slot 5, where is it going to go to? So on the top, it's 3 forward, on the bottom, it's 2 backwards. Straight forward, right? So in the bottom, where is it going to go to? From slot 5 to 3. I might not be able to keep up with the correct color combination, so do not hold me to it. There are too many colors, but I'll try my best. Oh, there will be a solid. The rest of it is simple. I'm just going to use a random color. I think I used blue. Okay. So from slot 3, where is it going to go on the top? Should be in your trigger memory by now. On the top, 180 degree apart. On the bottom, 2 slots behind. In case of 6-slot machine. On the top, where is it going to go? Anybody who hasn't answered so far? Want to take a guess? Get a point.
6.
Thank you. So on the top, goes into slot 6. On the bottom, it goes into slot 4. And then I'm giving up on the correct color to match it there. I'm just going to go with whatever I have in hand. Purple again. So from slot 1, slot 2, slot 3, slot 4. So what happens here though? From slot 4, where does it go? Slot 1, thank you, Ben. So I'm just going to continue the drawing there. So this is slot 1, right, which is right here for us. Slot 1. And then from slot 1, where does it go?
Slot 6.
Slots. Oh, it's going to go to slot 6 though. From slot 1, slot 6 is 1 slot behind, right?
Okay.
We need to go 2 slots behind.
Okay, so 5.
Slot 5. So on the top, it's going to be -2. On the bottom, it's going to be +3. For this particular configuration of simplex progressive lap winding, right? For different things, it'll be different and full pitch. So this +3 means full pitch. So if I had n number of slots, then you would go forward by a factor of n by 2. And then you would go back by a factor of n by 2 minus 1. Right? So that's pretty much the formula. So if you have n number of slots, even number of slots, this is what you're going to do for this particular way of winding the wire machine. Okay, so Christopher gave the answer where we go from slot 1 to slot 5 on the top. And then this in turn goes to slot 2 on the top. And then goes back to. Again, you don't have to draw this diagram in your notes. I have posted it on Canvas, the slides. You can just follow that along. I'm just doing it so you kind of get an experience as to how this is drawn. Right? And then final, this ends up terminating in slot 1 that we have here. Oh, sorry. I should use a different color. That is green. So from slot 6, it needs to go back to on the top, goes into slot 3. And where does slot 3 terminate? In the back? Slot 1. Right? So n by 2, so just 2 slots behind. And it terminates into slot 1. Okay. Symmetric. Right? Now let's go ahead and draw the commutators for these. Okay, so commutator. We're going to have a commutator segment here. At every bend, we are going to have a commutator segment. All of these are equally sized. The way I've drawn it, it doesn't look like it, but so there are a total of 6 segments. 1, 2, 3, 4, 5. The last one I've drawn it multiple times because this winding basically repeats here and here. But so this is commutator 1, commutator 2, commutator 3, commutator 4, commutator 5, and commutator 6. Right? So that would end up being this commutator 6. Right? The same red. It's the same red that's shown here. So they terminated the same commutator segments. Okay, so now let's start off with the case where the brushes are 180-degree opposite here and here. So these are the ones that connects us to the external world. So this is the winding diagram for a machine. So let's look at it in the slide. So a bit more clear. Right, so this was a winding diagram. So this is how you would, if I ask in the homework for the winding diagram, this is exactly how you would end up drawing it. So if you trace, right, so you start from slot 1. If you keep an eye on this blue conductor, starts from slot 1, goes into slot 4, comes out, goes back 2 slots behind, slot 2, comes out, goes forward 3 slots, slot 3, then comes back, goes slot 3, goes forward, comes back, goes to slot 4, and then goes around the loop, comes down here, and then comes up here, comes down here, comes up here, and then finally comes down here and terminates with slot 1 again, right? And then we have these commutator segments where there is a bend in the bottom side of the conductor at every single point, right? So now let's look at how the current flows through these conductors. So let's say I put a positive voltage. The current is now going to, so let's say I put 20 amperes here going into this motor. Then of course 20 ampere has to come back out of the motor. But once it goes to this commutator segment, it now has the option of 2 different pathways through which the current can flow, right? So these are called parallel paths. The current will split it equally through both the paths because there is no preference. All of these are exactly same length of wire, right? So both of them have same resistance, same inductance. So the current is going to split equally between the two. So 10 ampere goes to this side, 10 ampere goes to this side, right? So what I told before is I need to ensure that the current, so when I had 2 conductors in the same slot, the current going through this blue one and the current going through the purple one must end up being in the same direction. Otherwise, I'm in big trouble. If the current are in opposite direction, their net magnetic field in the slot is 0. There's going to be no torque produced. Motor is going to be useless. Right. So let's first trace out the current in the blue conductor. So current is going through this blue conductor in this direction, going through here, coming down through here. Right. We have already established one correct convention. So 20 ampere is coming out of this. That means 10 ampere is coming down from here. 10 ampere is coming down from here. And we can already quickly verify that the blue conductor current direction is downwards and the purple conductor current direction is also downwards in the slot 4, right? So one of the primary constraints is satisfied for us. So let's carry this forward. So we had our blue current coming here and then to slot 3 current is going up and then going here, going down here and then going here, going through the green conductor, coming down, and that is also verified. We assume that the current is coming down from the green conductor. It does end up actually coming down from the green conductor. All right, it was the same current, this 10 ampere that started off from the blue, went from the blue, did this full loop, went to the orange, did the full loop, went to the green, did the full loop, and came out of the commutator segment. So our previous assumption that the current 10 ampere is coming from there is in fact true because it was the same current that went into here. And it's also true because there is 20 ampere current coming out that has to come from 2 different pathways. Both have equal preference. So it's going to split 10 and 10. All right. So we verified that too. So let's look at the other pathway. So 10 ampere went one this way and then 10 ampere can go this side too. So goes into the brown conductor, right? In this direction, just follow the way I'm drawing it. then goes into this brown conductor. Again, at every point you see the current would be in the same direction. Right here also it's in the same direction, goes into the brown conductor, comes out here in the black conductor, again same direction, goes into this black conductor, comes down here in this black conductor, same direction as before, and then black becomes purple, right? Comes down the black conductor, goes up the purple conductor, it goes up the purple conductor. So coming from here, this purple is the same purple here. So comes up and goes out of the purple conductor. So we again ensured in the first law too, current is in the same direction on both sides. Alright. So these are called parallel paths. The way we have wound this, a lap winding, the number of parallel paths should be exactly same as the number of poles that we have in the machine. In our case, we have taken a simple case of a two-pole machine. If you put more number of poles, there will be more number of parallel paths for the current to flow through. There is another way of winding where here this conductor, so let me go to another diagram. So here I had started from slot 1, went forward, came down, went down. I needn't go back. I can actually turn this around and then wind it like this. So that is called a wave winding. It goes like a wave forward, right? And then it again, of course, it's a closed structure, so it will loop back again, right? But you can do this kind of winding too. So this winding has the advantage that irrespective of number of poles you have, the number of parallel paths will always be 2. So the way how you wind it, so again, this is very hard to visualize it. You'll typically have a program. You'll tell the number of slots, number of windings, and then it'll wind it for you and show you how it is laid out. You'll tell what configuration you want. And irrespective of number of poles you have, it will always be 2 parallel paths. All right. What will be the advantage of having more parallel? When will you use a motor with more parallel paths? When will you use the one with lesser parallel paths? So whenever you have a motor that's carrying a lot of currents, you would want to split the current as much as possible, right? You don't want a single conductor carrying too much current. That will make the conductor thickness very large. It will have a lot of heat, I square R, right? So if you can split that current into 2 different parts, so if you have 20 amperes, I square of 20 is much, much greater than 2 times I square of 10, right? So that will be 400. In this case, it will be 200. So you want to split it as much as possible. So very large motors with very high current going through them but low voltage would use these parallel paths. Of motors which have very large voltage, very low current would use the wave winding. In lap winding with higher pole count, there is a problem that is introduced called a voltage imbalance because as these rotor. Right. So in lap winding, so the rotor, the structure we have, it is basically resting on a ball bearing, right? So when we have this plot here. So we have these rotor structure, which is very large. And then we have these rotor segments, which is resting on a ball bearing. And then we have north pole here, south pole here, and then another north pole, south pole in the perpendicular direction of my drawing. Right? In these cases, what will happen is because of the weight of the rotor, it will sag a little bit down. So this rotor will be slightly closer to the pole on the bottom compared to the pole on the top. And this creates an unbalance in the voltage on the top conductor versus the bottom set of conductors. Right? So and this becomes even more, so what this will happen is when we have these parallel paths in a lap winding, you can have circulating currents between the 2 conductors because there's a difference voltage in the 2 conductors. So you'll have these circulating currents which are not producing any torque, it's being totally wasted. When you have these wave windings, there's only 2 parallel paths, there are no other additional parallel paths irrespective of how many poles you put. So you kind of get away with the problem of voltage imbalance that occurs, right? And that becomes a problem with especially large voltage motors. Right? So for this course, again, we'll look at very simple lap winding. We won't go into wave winding. You'll learn that in a machines design course if one such course is offered ever in this department. So this is the way we can draw the diagram again. So let's go back to my drawing on the board there. Maybe any questions so far? It's quite a bit of content that we have covered. Okay. So let me number this conductor 1, conductor 2, conductor 3, conductor 4, conductor 5, 6, 7 and 8, 9 and 10, 11 and 12. Okay. So I'm going to draw this in a circular manner. So Give me the answer for this. So starting from commutator 1, just tell me the diagram for. So commutator 1 is here. The brush 1 and sorry, brush for the, let's say, let me call this positive and the other one negative. So the positive is here and then the negative terminal is here. So once we are at the positive terminal, it splits into two pathways. Okay. So let's trace out this set of conductors going this direction. And then we'll do the same thing for this direction as well. So starting from here, just trace out the wire that I've drawn and just give me the number for the conductors alone, right? So there's the assignment. Can somebody tell me what the first conductor would be? What's the number for the first conductor that's coming out of the commutator that I've chosen? 1. And then it goes to conductor 8. Right? I'm going to draw it with an inductance because what this coil is basically a big wire, copper wire wound on a ferromagnetic material. We have created basically a solenoid. And there I just show one loop because of simplicity. But as we saw on the actual rotor, these are like n number of turns, like 10 or 20, 30 turns in every single slot. So it's a very large magnetic field that is being created, having a significant amount of inductance. There's going to be some resistance too, but for now, let's ignore it and model it as a pure inductive element because most of the resistance actually comes from the brush of a DC motor, not as much from the winding itself. Okay. From 8, where is it going to go to? 2. Thank you. And then 2 becomes?
Isn't it 3?
Oh, sorry, conductor 3. Slot number 2. Thank you. So slot number 2, but it goes to conductor 3 though, right? And then conductor 3 becomes? What's that?
10.
10. Perfect. And then the other one is again straightforward. So just goes up by 2, goes to 5, 10 goes to 5. And then I'm assuming 5 goes to 12. If I'm wrong, do let me know. Okay, so that is one parallel path, right? And then 12 comes back and terminates on the second commutator, right? So 12, right? So 12 terminates into the second brush, right? So that was the first parallel path. So current went through this, we traced out this path, went all the way, all the way, all the way, and then we traced it all the way back to this path. Now let's do the same for the other pathway. So going this way, all right, starting with conductor 6. So going in the backward direction might be a little bit confusing. So let's do it going this way, right? So starting from bottom brush, we are going to trace out the path. So first starts with 7, goes to, good luck giving the answer for that. I'm thoroughly confused, all right? 7 to 2, thank you. And then 2 to 9, perfect. 9 to 4. And then 4 to, you can already see the pattern here. 7, 9 and 11, right? And then 2, 4 and 6, right? So we end up with, oh, it's a nightmare shuffling between the cameras. All right, so we have 7 to 2, 2 to 9, 9 to 4, 4 to 11, 11 to 6. And then we need to double check that 6 is actually what is terminating on the brush outside, which is exactly what we have here. So conductor 6 is the one terminating on the top brush. Again, if you trace the path backwards too, it works either way, just a little bit more confusing. Yep, Christopher.
So 1 through 6 is on the bottom, and then 2, 4, 6, 8, 10, and 12 are the top.
Repeat that, sorry.
Are 1 through 6 on the bottom, and then the rest of the numbers on the top, or?
Yeah. So these are all, I wouldn't say top and bottom because as the rotor rotates, the position keeps changing.
Okay.
So for this way we have drawn it, you can think of it as these are all under North Pole. The first set of conductors are under North Pole, the second set is under the South Pole. So you can think of this as being under the influence of North Pole for now, and this set of conductors being under the influence of South Pole. Right? But then as the rotor rotates, the conductors under North Pole changes and the conductor on the South Pole changes. Right? Everybody clear so far? Any other questions? Okay. So we're going to see what happens as this rotor starts to rotate. Right, so this is the same diagram I put in the slides, but in a circular manner, just so that it's a little bit more intuitive, but this is typically how it's drawn. So we're going to stick with this convention in class, but homework you can do whatever is more intuitive for you, right? So now we're going to look at the case where the brush is moving forward, or in reality, the rotor is moving forward, right? So the rotor is going to be moving forward. So the brush is just going to slide past from commutator 1 to commutator 2, and then commutator 2 to commutator 3, so on and so forth. So initially the commutator was here, but then the commutator is now moving from commutator 1 to commutator 2, or basically the rotor is going in the other direction. So now the brush is in this new location, and this brush is in the new location, right? Can somebody tell me how this diagram would change? Is there any coil being shorted there? Which coil is being shorted? Which two conductors are being shorted? So when commutator 1 and commutator 2 are shorted, what are the two coils that are being shorted here?
1 and 8.
1 and 8, perfect. So the way we are going to draw is, let me first draw it, and then I'll explain what's going on. So 1 and 8, and then we have our brush shorting the conductor 1 and conductor 8. And then for the other commutator, what is being shorted? C4, C5. C1, C2 is being shorted by the brush, and C4, C5 is also being shorted by the brush. What two conductors are it shorting?
2 and 7.
2 and 7. So you can already see the pattern coming out. Okay, so we have 2, 7, and now the brush is shorting these two. And then the rest of the conductor is pretty straightforward to draw. We can go through the same process again, trace that. But if you can see what's going on here, it's basically these set of coils are rotating, right? As they rotate, these two got shorted, and these two got shorted. These rest of the coil set just moved around. So we have 3 and 10 now here. And then we have 5 and 12 here. We have 6 and 11. And then 4 and 9. Yep. Right? Everybody clear on this part? So right away you can see previously, these whole bunch of coils, 6 set of coils are producing torque and producing EMF. Now these two coils are shorted. But then there are other set of coils that are still producing EMF. So this was the diagram I drew in the beginning, right? When Thomas asked what the EMF would look like when you have multiple coils. Right? The tiny dip is because one set of coil is not producing EMF at this point. The rest whole batch is producing EMF. If you have say 100, not 100, but if you have say 12 slots in the motor, as the case we had in our rotor for our lab motor, you have 12 of these, 6 on one side, 6 on one side. At any given time, even when so typically you would have 6 here, 6 here, but when the commutator action is acting, you would have 5 here, and then 1 and 1 on the top and the bottom being shorted. Right? So there will be only a tiny dip. In our case, the dip would be a little bit more prominent because 1/3 of the coil has gone out of picture, so the voltage you better drop it by 1/3. But if you have 6 coil, and in that case, 1/6 of the coil would be dropped out. So the voltage you can expect drops by a factor of 1/6. Right? If this is 1, this is 1, right? 1 minus 1/6, so minus 1/3. So, and again, we can draw the parallel pathways for the current. Split like this, and then come back, collect on the bottom, come back and collect on the bottom. How will you draw for the rest of the diagram as the commutator, as the rotor rotates and the commutator moves? What do you do? Basically, just keep rotating this winding, right? So 1 and 8 will come to the left, 6 and 1 will come below it, so 4 and 9. So all you have to do is just change this numbering. 6, 11, 4, 9, 2, 7. 6, 11, 4, 9, 2, 7. I forgot what I deleted there. 12 and 5. 10 goes with 3, and then 1 goes with 8. Right? So basically, whatever we had here, just rotate it. This would be the scenario where, I'll just take one more minute. This would be the case once the brush moves fully placed on commutator 2 and then commutator 5. And then again, after some time, I'm going to short C to C3, rotate the winding again, and then this keeps repeating again and again and again. Right? So when we are shorting this coil, is this going to be a problem?
I mean, is there gonna be current flowing in the coil?
There is going to be, if you're shorting a conductor that's carrying current, that's fine. Right? You don't want to interrupt a conductor that's carrying current. It's absolutely fine shorting a conductor. Then you can have an inductor and you can short an inductor, right? That's what a freewheeling diode and a buck converter that we saw does. When you break the switch open, the diode is basically shorting the conductor. That's absolutely fine. What is the bigger problem? What shouldn't you short? The voltage, you need to ensure that the coil voltage across 2 and 7 and 1 and 8 is close to 0. Alright, that's the requirement. So when we created our magnets, we will put it in such a way that it only covers a portion of these conductors and doesn't cover 1 and 2 and 7 and 8. Alright, so that's why when we had our magnets, the correct angle, our magnets didn't stretch all the way. Right? Our magnets only stretched to like 60 degrees. So this was our north pole and this was our south pole. Okay, or whatever angle that comes out to. So if you see 1 and 2 and 7 and 8 are in between the region where the magnetic field is very close to 0. Alright, so in addition, the windings would be at 90 degree at that point. So when the windings are at 90 degree, we saw that the flux would be maximum, so d phi by dt would be 0. So the EMF across the coil that's being shorted would be very close to 0. Alright, so this is what we want to ensure happens in ideally, but in reality, we'll see that that's not what happens. Even though the magnet does not have the full coverage, even though the flux is not changing at that point, there would still be some kind of voltage induced in that winding due to armature reaction, which will become a bit problematic. There is another problem when we break this contact, going from, when we moved from 1 to 2, there was current previously in this conductor. Now the conductor current is breaking and moving to C2. Right? We are still interrupting a current. That would be a problem. So that commutation, we need to ensure that the current does completely transfer from one direction to the other when the breaking happens, all right? Which we will do when we meet after spring break, but on Wednesday we'll do a review class, right? That's clear.